Hello everyone, welcome to lecture series on functional analysis. In our last lecture, we have seen that some basic definition of functional analysis. So let's continue with this definition. Here, new definition is function space C with closed interval AB. So for that, first you have to take set X, which is a set of all real valued functions x, y, which are functions of an independent real variable t. It means if you are taking some element from C of AB, which is one type of function, and with variable t, and are defined and continuous on a given closed interval. Suppose I say j is equal to closed interval AB. Next, choosing the matrix defined by d of xy is equal to maximum of modulus of x of t minus y of t, where t belonging to given interval j, where max stands for maximum, and we obtain a metric space which is denoted by C closed interval AB, and letter C stands for continuous. Right, so function space C closed interval AB is what? In this space, elements are function. Which type of function? Function which is continuous and having with one variable. Suppose it's t. So this is a functional space. Why we are called it function space? Because in this space elements are function. So we are called it as function space C closed interval AB. Next definition is discrete matrix space. For that, we have take X and define a metric on the set X, and XD is called a discrete matrix space if discrete matrix for X defined by dxx is 0 and dxy is 1, but here is condition, that is x is different from y. In that condition dxy will become 1. So this set, and with this metric our xd is also a metric space. Next definition is sequence space S. So sequence space of the set of all bounded or unbounded sequences of complex numbers, and the metric d defined by dxy is equal to summation over j is equal to 1 to infinity 1 upon 2 raised to j uh, con, uh, in modulus xj minus yj upon 1 plus modulus xj minus yj, where my x is sequence xj and y is also sequence yj. So x is sequence xj means what? x1 x2 up to infinity, and y equal to yj means if I am wearing put the value of here y, so that is y1 comma y2 comma up to so on. So sequence space is what? All these bounded and unbounded sequences of complex number, and the we define metric like this. So this space S with this metric D, xd is metric space. Again, sequence space. What is sequence space? In sequence space elements are sequence, so it called it as sequence space. Which type of sequence? It is may bounded or may not be unbounded, or may unbounded or may not be bounded. So if I am taking any element from this space S, all elements are type of sequence. Next, we have to prove that this sequence space N with this matrix D is matrix space. So for that, first three properties, that is first real valued function, D is real valued function, and positive D is positive, right, is obvious. Next property third property and second property. Very easy to prove. We are going to prove only fourth property, that is dxy is less than or equal to dxz plus dzy. So for that I am taking three elements, these three elements from the space, right? So x, y and z. So x is equal to xi means I am taking one sequence xi, that is x1, x2 up to so on, and another is y, will become y1, y2 up to y, so on, and that is z1 comma z2, right, belonging to a sequence space. For that we use auxiliary function f defined on real number r, as f of t is equal to t upon 1 plus t. When I am differentiating this function, f of t will give f dash of t, and denominator as it is, differentiate numerators, differentiate of t is 1, and numerator t as it is, and differentiate 1 plus t, that is 1, and denominator, square of denominator, so that is 1 plus t whole square. Here plus t minus t will get cancelled and will become 1 upon 1 plus t whole square, and which is greater than 0. So hence f is monotone increasing function. How? Because its differentiate, first differentiate is positive, and my t function is increasing, so it is monotonic increasing function. And we know that the property of this is modulus property, that is modulus of a plus b less than or equal to modulus of a plus modulus of b. When I am applying f function on this equality will become f of modulus of a plus b less than or equal to f of modulus of a plus modulus of b. So here f of, we define f of t is equal to t upon 1 plus t. So instead of t here I have modulus of a plus b. So what was the value of this function? That is modulus of ab upon 1 plus modulus of ab less than or equal to as it is. And here instead of t I have modulus of a plus modulus of b. So apply the definition of this function will give modulus of a means t, it means modulus of a plus modulus of b, 1 plus t, it means 1 plus modulus of a plus modulus of b. So next, modulus of a upon 1 plus modulus of a plus modulus of b upon 1 plus modulus of b, which greater than or equal to, I can write it as modulus of a plus b upon 1 plus modulus of a b. Next, I'm letting xi a is equal to xi minus zi and b equal to zi minus yi. And we know that what is zi? So z is equal to zi. When I am adding a plus b, so a plus b is equal to, put the value of a, that is x minus zi, and put the value of b, that is plus zi minus yi. So minus zi plus zi get cancels and will become xi minus yi. So value of AB will become xi minus yi. So put all this value in this inequality. We get modulus of A. So A is xi minus zi. So modulus of xi minus zi. 1 plus modulus of A. So value of A is xi minus yi. Right. When I am putting all these values in this equation will become modulus of xi minus yi upon 1 plus modulus of xi minus yi less than or equal to modulus of xi minus zi upon 1 plus xi minus zi plus zi minus yi, 1 plus modulus of zi minus yi. If we multiply both sides by 1 upon 2 raised to I and sum over from 1 up to infinity, we get, first we are multiplying both by 1 upon 2 raised to I. So it is 1 upon 2 raised to I here, and here 1 upon 2 raised to I, and also here 1 upon 2 raised to I. And then put this summation here and here. So it is summation I is equal to 1 upon 1 to infinity, and here and here. So this is the triangular inequality with our metric, that is summation I is equal to 1 to infinity 1 upon 2 raised to I modulus of xi minus yi upon 1 plus modulus of xi minus yi. And from this fourth properties, we can say that my SD is metric space. So next example is space of bounded function, uh, which we have denoted by B of A. So in this space, all elements are functions. Which type of function? It is bounded on a given set A. So metric is defined by on this set is dxy is equal to supremum of modulus of f of x of t minus y of t, but t belonging to A. And we know that SUV denotes the supremum, and also we write this space as B of closed interval AB for BA, where A is subset of my real number R, and suppose you can write it as here A is equal to closed interval A B. So please here make sure that if I have space C with closed interval AB, so this is the space. In this space all functions are continuous, right? But here B closed interval AB, in this space my functions are bounded. So this is the difference between C of closed interval AB and B of closed interval AB. So remember this. Next is vector space over K, and where K is my field, and I'm taking this field as R or C. R is a set of real number and C is a set of complex numbers. So definition of vector space over K is a triple V plus dot, where plus is plus and dot. Plus is addition and dot is scalar multiplication. So here plus is the function and defined as V cross V, 2V called addition. How we define it as, if I am taking V and W, small v and W belonging to this capital V, so V comma W, and I am applying this function plus, so it become V plus W. Similarly for scalar multiplication, if I have K, why it's scalar? Because I am taking scalar from this field, so it is K cross V, 2V is called scalar multiplication. And how it defined? That is alpha V to alpha V. It means alpha into V, scalar multiplication. So for vector space, first V plus is an abelian group, and distributive property, that is alpha of V plus W is equal to alpha V plus alpha W, alpha belonging to in field and small v and small w in belonging to capital V. And third one is alpha of BV is equal to alpha B into V and B into alpha V, where my alpha and beta in this field, it means both are scalar and V belonging to V, so V is factor, and 1 into V is V, so V belonging to V. If these four property are satisfied with this addition and scalar multiplication, I'm saying that this V plus dot is vector space, right? Here the elements of V are called vectors and the elements of K are called scalars. So this is all about vector space. Uh, I have to prove vector space, any space to vector space. For that, I proved that these four properties. So next definition is vector subspace. So for that, we have taken some vector space over some field. So I have taken V plus dot is a vector space over field K, and I am taking here Y is subset of V. is said to be a vector subspace of this vector space if y plus dot is a vector space over K with same addition and scalar multiplication which defined on this vector space. Right. When we say that this is a vector subspace of this y plus dot is itself a vector space over field K with this same addition and scalar multiplication. Or equivalently, you can say that if y is closed under plus and dot, you know that the closure property, right? That is alpha v plus beta v belonging to y, where these are scalars and these are vectors. So note that y and only this 0 are vector subspace of v plus dot called improper subspace of v plus dot, and if my y is different from 0 and different from v is called proper subspace of v plus dot. So here is improper and proper subspace of vector spaces. Next is linear space of M, linear span of M subset Y. For that, I'm taking some vector space over K. So here is vector space V plus dot over this field, and phi is different from M, and my M is subspace of Y. M is subspace of V, and here is also M is subspace of V. The linear span of M, or you can simply span of M denoted by span M and defined by span M is equal to take linear combination with this vector and scalars where n belonging to n, my scalar belonging to in this field, and this vector belonging to this subspace. So if I am taking linear combination, that is alpha 1 x1 plus alpha 2 x2 plus alpha plus so on alpha n xn, it means I am writing this vector as a linear combination of all these vectors in M, right? So it becomes a span of M, the set of all finite linear combination of elements of M. So here note that span M is a vector subspace of a given vector space and is smallest vector subspace of V plus dot containing M. Next is Hamel basis or basis. This all definition you have learned in your BSc, right? So this is just revision. So V plus dot is a vector space over field K, and phi is different from M is subset from V is said to be a Hamel basis, or you can say that basis of given vector space V if there are satisfied two conditions. First one is M is linearly independent, and second one is span of M is whole of my vector space V. So whenever I say that the set of vectors are bases, if this set of vectors satisfy these two conditions, that is first one is this M is linearly independent and span of M is whole become vector space V. Next definition is linearly dependent and linearly independent set. So I have taken vector space over field K and some elements from V, that is x1 x2 up to xn belonging to V. These vectors are said to be linearly independent vectors if I am taking some scalars alpha I belonging to K. With this I is equal to 1 to up to n, and taking linear combination, that is alpha I x I alpha 1 x1 plus alpha 2 x2 plus so on plus alpha n xn is equal to 0. If my all scalars become 0, then I'm saying that these my vectors are linearly independent. When I'm saying that these vectors are linearly independent, first I have to take linear combination with the scalars, and by solving this linear combination I'm getting all alpha all alpha are 0. So I'm saying that these vectors are linearly dependent. So next definition is linearly independent. So those vector these are not linearly independent is called linearly dependent. So for linearly dependent, also you can say that there exists alpha 1, alpha 2 up to alpha n belonging to some field K, not all 0 such that this linear combination gives 0. It means if I am taking this linear combination, and in this linear combination, if any one alpha give is not 0, right, not all 0, any one alpha is has some value which is different from 0. So for in this case I am saying that x1 x2 up to xn are linearly dependent vectors. So here M is subset of V is said to be linearly independent if every finite subset of M is linearly independent. So this is the definition of linearly independent. And you can say that M is subset of V is said to be linearly dependent if M is not linearly independent. So here is definition of linearly dependent. Next one is cardinality. So when M said that the cardinality of set A is n or m. So if I have a set A which is a finite set, then cardinality of A is denoted by like this, card of A. And what is the cardinality of A is the number of element in A is called cardinality of A, right? Again, cardinality of A is the number of element in A. Next, two such sets A and B are said to have same cardinality if there exists a bijection map F from A to B. You know that what is the bijection, that is 1 1 and onto map. If I have two set A and B, and I'm saying that that set have a same cardinality, it means cardinality of A is equal to cardinality of B. When I'm saying that this happen if there exists a bijection map F from set A to set B, then I'm saying that this two set have same cardinality. So here is some notes. The cardinality of countable set is alpha naught. You can read it is alpha naught, right? And must note that countable set has cardinality alpha naught. It is a standard notation alpha naught, right? Next is the cardinality of R is C. Also note that this C is not the complex number, complex plane. It is simply C, right? And here this R is set of real numbers, and this C is, again I'm repeat this C is not complex plane. It's just simply C, any number, and this is also standard notation for cardinality of R, right? And the cardinality of all polynomial over this R, it is 2 times 2 power C. Here all polynomial with R. Next, some result over vector space. So that is V, which is vector space over the field K and different from zero vector. Then V has a basis, and the cardinality of uh, a basis of V is called the dimension of that vector space V, and it is denoted by dimension of V. You know that how you show that the any vector space have dimension n. For that you can take the basis and you can count how many elements in basis. So there are bases which can show that how many bases. Suppose two bases, so my dimension of V is 2, right? So dimension of any vector space is depend on its basis. Next definition is finite dimensional vector space. So I have a vector space over field K and is said to be a finite dimensional vector space if it is has finite basis, right? Finite basis means finite dimensional because dimension is depend on basis. So here is one example. Suppose I am taking k to the power n is a vector space, and which type of element in this space k to the power n, here is described the set that is all ordered n tuples x1 x2 up to xn, where xi belonging to k and I is running from 1 to n. Then k to the power n is a vector space with respect to coordinate wise addition and scalar multiplication. So here also define you have coordinate wise addition. So for that I am taking two elements in this space Kn, x1 up to xn and y1 up to yn belonging to Kn. So coordinate wise as the addition is defined as first coordinate plus here first coordinate, that is x1 plus y1. Here is second coordinate, take second coordinate, that is x2 plus y2, and so on. Last coordinate and last coordinate. So here is xn plus yn. This is coordinate wise addition. And next one is coordinate wise scalar multiplication. For that I have taken one vector and one scalar. So alpha in this scalar become alpha 1, alpha x1, alpha x2 and alpha xn. So it is easy to check that kn plus dot is a vector space. If I want to show that this is a vector space, for that I have to show that four properties abelian group and remaining 3 over this k. And you know that 0 0 0 is the zero vector of this vector space. If I am taking e1 e2 en, all are basis for basis of kn. So standard unit vector, that is 1 0 0, and e2 for second coordinate is 1, and en last coordinate is 1. So if I am putting all these as an vector, that is e1 e2 en is a basis of kn. So it means there are n elements in this basis. For it means dimension of this vector space is n. So kn is finite dimensional vector space over k. Have you saw that is any vector space has n dimensional. So for that first take basis, and first you have to prove that this is the basis for this vector space, right? So here is standard basics, standard elements, and we easily show that these vectors are linearly independent and also span uh, with this k to the power n. So this is basis, and there are n elements in this basis, so that we can say that dimension of kn is n. So Kn is finite dimensional vector space over K. Next is our result for finite dimensional vector space, that is V be a finite dimensional vector space over K of dimension n, and I'm taking vector x1 x2 up to xn belonging to this vector space Kn, which are linearly independent, then this vector xm can be extended. You can extend this vector as a basis such as x1 up to xm, comma xm plus 1 up to so on xm plus n of V. If W is a proper vector subspace of V, then you can say that dimension of W less than dimension of V. So this result and these definitions are useful in our functional analysis. So in our next lecture, we are going to start norm linear space, and for that we have defined norm for any linear space. So first, for that we have remember this all things which we have learned in our first and this second lecture, right? So in next lecture we are going to start our unit 1, that is norm linear space. So thank you.